Today we will discuss about the control of microgrid. The operation and control of microgrids is controlled and coordinated by two controllers. One is called microsource controller and the other one is called central controller. So we will see the central controller first. Microgrid central controller or central controller is responsible for the overall control of the system. It can maintain power quality, can provide power dispatch and alter set points for all MCs and coordinate protection. It has two functional modules, Energy Management Module abbreviated EMM and Protection Coordination Module PCM. Energy Management Module abbreviated EMM. It is the duty of Energy Management Module to provide set points for frequency, voltage, real and reactive power output to each microsource controller. Protection Coordination Module, it responds to microgrid, main grid faults and loss of grid scenarios in a way so as to ensure correct protection coordination of the microgrid. This PCM also helps to resynchronize the microgrid to the main grid after the initiation of switchover to the grid-connected mode of operation through suitable reclosing schemes. Coming to microgrid management, a wide range of control is necessary to ensure system security, optimal operation, emission reduction, and smooth transfer between operating modes without violating system constraints and regulatory requirements. The central controller and microsource controller takes care of these tasks. The central controller executes the overall control of microgrid operation and protection to the microsource controllers. Its main function is to maintain power quality and reliability through power frequency control, voltage or reactive power voltage control, and protection coordination. The central controller also provides the power dispatch and voltage set points to all MCs. Functional modules of central controllers are Energy Management Module and Protection Coordination Module. Energy Management Module. The network management needs of a microgrid are met by Energy Management Module with the support from PCM and microsource controllers. So Energy Management Module performs microsource generation control, domestic process control like HVAC, heaters, chillers, blowers, etc. Energy storage control, that they do ensure uninterrupted power supply to priority loads and they can maintain power quality. It also performs regulation and load shifting. At every moment, generation and load should be matched. This is achieved by scheduling of loads, charging of energy storage devices, and shifting individual load peaks. And during standalone mode, Energy Management Module needs to maintain supply to priority loads. And it is also responsible to provide valuable ancillary services to utility, especially when grid is under stress. This microgrid can provide support to participate in open market. Coming to microsource controller, operation and control of microgrids is controlled and coordinated by this microsource controller and central controller. So the microsource controller are fitted on microsources and storage devices to execute smooth and flexible operation of these devices to meet customer and utility requirements. They may operate with or without any intervention of the central controller. The microsource controller is responsible for the control of voltage profile at the load end. It also participates in economic generation, load tracking or management, and demand side management. It is responsible to supply its share of its generation at standalone mode. The most significant aspect of microsource controller is its quickness in response to the locally monitored voltage and currents irrespective of the data from the neighboring MCs. It will override the CC directives that may seem dangerous for its microsource. Now the built-in control features of the MCs are real and reactive power control, voltage control, storage requirement for fast load tracking, load sharing through power frequency control. Let's see the first one, real and reactive power flow control or PQ control. We need to control microsource so that its real and reactive power output is constant. This is called PQ control. Figure shows the basic scheme for a typical MC consisting of the microsource and the power electronic converter. VSI is the converter system, controls both magnitude and phase angle delta 1 of the output voltage V angle delta 1 at bus terminal 1 or converter terminal. The microsource supplies is control power to the bus 2 microgrid bus at an voltage of E angle delta 2 through an inductor of reactance X. Usually V angle delta 1 leads E angle delta 2 by the power angle delta given by delta is equal to delta 1 minus delta 2. So by controlling the delta, the real power is controlled, and by controlling the voltage, reactive power is controlled. So we know that the voltage deviation is mainly due to the mismatch between reactive power generation and consumption, whereas the frequency deviation is mainly due to the mismatch between real power generation and consumption. And the controls are mainly based on feedback loops of output power P and E. The equations for P and Q is given by P is equal to 3VE by 2x sin del and reactive power is equal to 3VE by 2x into V minus E cos del. Let's see the voltage control. Why voltage control of microgrid bus is essential. Apart from active and reactive power flow control, microgrid bus control is also required for overall reliability and stability of microgrids. Without suitable voltage control, microgrids with huge number of microsources might undergo reactive power oscillations. Like big synchronous generator, voltage control function of MC deals with the issue of reducing huge circulating reactive currents between microsources. The large impedance between generators limits the circulating current in utility grid. But in the case of microgrids, even this issue becomes comparatively prominent since the feeders are generally radial with small impedance between the sources. Even with slight differences in their voltage set points, these circulating currents may also go beyond the rated currents of microsources. How to control this circulating current? Actually, the circulating currents can be controlled by using voltage reactive power or droop controllers with droop cara. And here you can see the figure. It shows the droop cara for VQ droop controllers. This controller, it increases the local voltage set points when the microsource reactive currents become predominantly inductive and vice versa. The purpose of the droop controller is to decrease the local voltage set point when the microsource reactive currents become capacitive and to increase the set point when the current become mostly inductive. The reactive power limits is set by P output of the microsource and the VA rating of the inverter, and as given by the equation Qmax is equal to root of S square minus P square. So let's see the third one, storage requirement for fast load tracking. In case of grid connected microgrid, utility generators take care of its initial power balance throughout the connection of new loads. However, the microgrid must ensure initial power balance through its storage devices for standalone operation. Hence, fast load tracking in standalone mode is made possible with the help of storage devices in microgrids. The DC storage devices are connected to the DC bus of the microsource, while the AC storage devices are directly connected to the microgrid bus. This microsource controller MC ensures proper utilization of the storage devices for fast load tracking. So there should not be any power balancing issue. The fourth one is load sharing to power frequency control. Microgrid controllers guarantee automatic and smooth changeover between different modes as per the requirement. Local power balance at the new loading during changeover from grid to standalone mode is achieved by changing the operating point by asserting local power frequency control to MC of each microsource. After tracking load properly, the controller does this autonomously without waiting for any command from neighboring MCs or the CC. So, depending upon the consumer requirements, microgrid loads are supplied from the microsources and utility grid during grid connected mode. When utility grid supply is interrupted due to any disturbance or contingency, the microgrid switches over to standalone mode. And during the changeover process, the voltage phase angles of the microsources also changes, leading to a clear drop in their output power and local frequency. So without any new power dispatch schedule from the central controller, the microsource rapidly pick up its load share. The power versus frequency data of two microsources is shown here. So here you can see these two microsources, they are operate at a common minimum frequency of omega minimum with maximum capacity P1 max and P2 max. In grid connected mode, they operate at a base frequency of omega 0 delivering power P01 and P02. So with the variation in load, the microsources work at different frequency, causing an alteration in the power angles, and the operating frequency moves to a lower common value with different proportions of load sharing. And since the microgrid frequency decreases with droop regulation, this microsource controller must integrate control functions to re-establish the operation at rated frequency with correct load sharing.